Dear students, I welcome you in the last lecture from the topic Projections on Hilbert spaces. In this lecture, we will prove the theorem. Let us see the theorem. The statement is, let P1, P2, Pn be projections on closed linear subspaces M1, M2, Mn of H respectively. Then P is equal to P1 plus P2 plus Pn is a projection if and only if Pi's are pairwise orthogonal, in the sense that Pi composition Pj is equal to 0 whenever I is not equal to j. And in this case, P is projection on M, where M is defined as M1 plus M2 up to Mn. So it is sum of all these linear spaces. So first part, this is a lengthy proof, and we are going to divide proof in smaller parts for better understanding. So in first part of the proof, let us prove the result that P is idempotent if and only if P is projection. So consider P is equal to P1 plus P2 plus Pn. Then P star will be equal to P1 star plus P2 star plus Pn star. Since Pi star equals to Pi, as Pi is projection, we have the result that P star is equal to P1 plus P2 plus Pn. So this implies P star is equal to P. This implies that P is self-adjoint. So P is idempotent, because if P is equal, then we clearly have P square is equal to P. So this is true if and only if P is projection. Further, these steps can be reversed back, that you note. So thus, what result we have proved here? P is idempotent if and only if P is projection. So this result we have proved as a beginning of first part. Now let us go through the second part. So in second part, we assume that Pi's are pairwise orthogonal, that is Pi composition Pj is equal to 0 if I is not equal to j. So consider P square is equal to P1 plus P2 plus Pn square. As they are pairwise orthogonal, we can easily observe that this evaluates to P1 square plus P2 square plus Pn square. And since these are projections, we have this is equal to P1 plus P2 plus Pn, which is equal to P. So P square is equal to P, that is P is idempotent. So from the first statement, we can write that P is projection. Thus, in second part, we have proved the result that if Pi's are pairwise orthogonal, then P is projection. Now, in third part, we will prove that if P is projection, then Pi's are pairwise orthogonal. So in order to prove this, let P be a projection. So we assume that P is projection. Then again from first, P is idempotent. Recall that in first part we have proved that P is projection if and only if P is idempotent. Let X be a vector. Let X be a vector in the range of Pi. Then Pix is equal to X, as Pi is projection. So consider norm of x square. You can easily observe that this is equal to norm of Pix square, because P is projection. So here it should be actually I is equal to, or say J is equal to 1 to n Pix. So note this correction, Pix square. By triangle inequality, here we are using triangle inequality. This will be less equal to summation J is equal to 1 to n, summation J is equal to 1 to n norm of Pjx square. This is equal to summation J is equal to 1 to n Pjxx, because Pj's are projections. So this is nothing but this I could write as J is equal to 1 to n Pjx and its inner product with x. So that is nothing but equal to inner product of Px and x, and that equals to again norm of x square. So thus we proved, if you observe, we begin with norm x square and we obtain that it is less equal to norm x square. So whatever arguments we have in between, all those will be equal to norm Px square equals to x. So we can now conclude that from the foregoing arguments, we can now conclude that norm of Pjx square equals to norm of Pix square, and hence norm of Pjx is equal to 0 if j is not equal to I. In other words, we have proved that range of Pi is subset of kernel of Pj for every j which is not equal to I. That is, Mi is subset of Mj perpendicular. This by previous theorem. In previous theorem we proved that if the set M is orthogonal to n, then PQ is equal to 0. Then by previous theorem we can get that Pi Pj must be 0 if j is not equal to I. So in the third part we proved the statement that if P is projection, then Pi's are pairwise orthogonal. So from second and third, now we can conclude that if P is projection, then Pi's are pairwise orthogonal. In last part of the proof, we are going to prove that P is projection on M. So in order to prove that P is projection on M, first understand what is P and what is M. P is sum of all these projections P1, P2, Pn, and M is sum of all these linear spaces. So consider the fact that if P is projection, then we will have norm Px is equal to norm x for every x in MIs. So Mi is going to be a subset of range of Pi for all i's. This implies that sum of M1, M2 and Mn is subset of range of P1 plus P2 plus Pn. So M is range of P. M is subset of range of P. In the next argument, consider if x is in range of P, then Px is equal to x. This implies that P1x plus P2x plus Pnx is equal to x. This implies that x is equal to P1x plus P2x plus Pnx. Now this clearly belongs to P1x belongs to M1. Similarly, Pnx belongs to Mn. So x clearly belongs to M1 plus M2 plus Mn. But M1 plus M2 plus Mn equals to M. So thus x belongs to M. We proved that if x belongs to range of P, then x belongs to M. So range of P is subset of M. From whatever we have proved so far, we could write range of P is subset of M. Range of P is subset of M. So this proves our argument that P is projection on M. This is what we wish to prove. in the theorem. We have divided proof in 4 parts, and I have given you a very clear-cut proof in notes which I have discussed here. This completes the second chapter, Hilbert spaces. Thank you.